an elementary course in Synthetic Projective Geometry by Derek Norman Lehmer. Chapter 8 continued, Involution. Section 131, Involution of points on a point row of the second order. Section 132, Involution of rays. Section 133, Double rays. Section 134, Conic through a fixed point, touching four lines. Section 135, Double correspondence. Section 136, Pencils of rays of the second order in involution. Section 137, Theorem concerning pencils of the second order in involution. Section 138, Involution of rays determined by a conic. Section 139, Statement of theorem. Section 140, Dual of the theorem. Problems. Section 131, Involution of points on a point row of the second order. It is important to note also in Steiner's construction that we have obtained 2 point rows of the second order superposed on the same conic, and have paired the points of one with the points of the other in such a way that the correspondence is double. We may then extend the notion of involution to point rows of the second order and say that the points of a conic are paired in involution when they are corresponding points of 2 projective point rows superposed on the conic, and when they correspond to each other doubly. With this definition, we may prove the theorem. The lines joining corresponding points of a point row of the second order in involution all pass through a fixed point U, and the line joining any 2 points A, B meet the line joining the 2 corresponding points A', B' in the points of a line U, which is the polar of U with respect to the conic. For take A and A' as the centers of 2 pencils. The first perspective to the point row A', B', C', and the second perspective to the point row A, B, C. Then, since the common ray of the 2 pencils corresponds to itself, they are in perspective position, and their axis of perspectivity, U, figure 38, is the line which joins the points AB', A'B to the point AC', A'C. It is then immediately clear from the theory of poles and polars that BB' and CC' pass through the pole U of the line U. Section 132, Involution of rays. The whole theory thus far developed may be dualized, and the theory of lines in involution may be built up starting with the complete quadrilateral. Thus, the 3 pairs of rays which may be drawn from a point through the 3 pairs of opposite vertices of a complete quadrilateral are said to be in involution. If the pairs AA' and BB' are fixed, the line C describes a pencil, the corresponding line C' also describes a pencil, and the rays of the pencil are said to be paired in the involution determined by A and A'. Section 133, Double rays. The self-corresponding rays, of which there are 2 or none, are called double rays of the involution. Corresponding rays of the involution are harmonic conjugates with respect to the double rays. To the theorem of Desargues, section 125, which has to do with the system of conics through 4 points, we have the dual. The tangents from a fixed point to a system of conics tangent to 4 fixed lines form a pencil of rays in involution. Section 134. If a conic of the system should go through the fixed point, it is clear that the 2 tangents would coincide and indicate a double ray of the involution. The theorem therefore follows. 2 conics or none may be drawn through a fixed point to be tangent to 4 fixed lines. Section 135. Double correspondence. It further appears that 2 projective pencils of rays which have the same centers are in involution if 1 pair of rays correspond to each other doubly. From this it is clear that we might have defined 6 rays in involution as 6 rays which pass through a point and also through 6 points in involution. While this would have been entirely in accord with the treatment which was given the corresponding problem in the theory of harmonic points and lines, it is more satisfactory from an aesthetic point of view to build the theory of lines in involution on its own base. The student can show, by means entirely analogous to those used in the second chapter, that involution is a projective property. That is, 6 rays in involution are cut by any transversal in 6 points in involution. Section 136. Pencils of rays of the second order in involution. We may also extend the notion of involution to pencils of rays of the second order. Thus, the tangents to a conic are in involution when they are corresponding rays of 2 projective pencils of the second order superposed upon the same conic, and when they correspond to each other doubly. We have then the theorem. Section 137. The intersections of corresponding rays of a pencil of the second order in involution are all on a straight line U, and the intersection of any 2 tangents AB, when joined to the intersection of the corresponding tangents A', B', gives a line which passes through a fixed point U, the pole of the line U with respect to the conic. Section 138. Involution of rays determined by a conic. We have seen in the theory of poles and polars, section 103, that if a point P moves along a line M, then the polar of P revolves about a point. This pencil cuts out on M another point rho, P', projective also to P. Since the polar of P passes through P', the polar of P' also passes through P, so that the correspondence between P and P' is double. The 2 point rows are therefore in involution, and the double points, if any exist, are the points where the line M meets the conic. A similar involution of rays may be found at any point in the plane, corresponding rays passing each through the pole of the other. We have called such points and rays conjugate with respect to the conic. Section 100. We may then state the following important theorem. Section 139. A conic determines on every line in its plane an involution of points, corresponding points in the involution being conjugate with respect to the conic. The double points, if any exist, are the points where the line meets the conic. Section 140. The dual theorem reads, a conic determines at every point in the plane an involution of rays, corresponding rays being conjugate with respect to the conic. The double rays, if any exist, are the tangents from the point to the conic. Problems. 1. 2 lines are drawn through a point on a conic so as always to make right angles with each other. Show that the lines joining the points where they meet the conic again all pass through a fixed point. 2. 2 lines are drawn through a fixed point on a conic so as also to make equal angles with the tangent at that point. Show that the lines joining the 2 points where the lines meet the conic again all pass through a fixed point. 3. 4 lines divide the plane into a certain number of regions. Determine for each region whether 2 conics or none may be drawn to pass through the points of it and also to be tangent to the 4 lines. See section 144. 4. If a variable quadrangle moved in such a way as always to remain inscribed in a fixed conic, while 3 of its sides turn each around one of 3 fixed collinear points, then the 4th will also turn around a 4th fixed point collinear with the other 3. 5. State and prove the dual of problem 4. 6. Extend problem 4 as follows. If a variable polygon of an even number of sides move in such a way as always to remain inscribed in a fixed conic, while all its sides but one pass through as many fixed collinear points, then the last side will also pass through a fixed point collinear with the others. 7. If a triangle QRS be inscribed in a conic, and if a transversal S meet 2 of its sides in A and A', the 3rd side and the tangent at the opposite vertex in B and B', and the conic itself in C and C', Then AA prime, BB prime, CC prime are three pairs of points in an involution. 8. Use the last exercise to solve the problem. Given 5 points Q, R, S, C, C prime on a conic, to draw the tangent at any one of them. 9. State and prove the dual of problem 7 and use it to prove the dual of problem 8. 10. If a transversal cut two tangents to a conic in B and B prime, their chord of contact in A, and the conic itself in P and P prime, then the point A is a double point of the involution determined by B, B prime and P, P prime. 11. State and prove the dual of problem 10. 12. If a variable conic pass through two given points P and P prime, and if it be tangent to two given lines, the chord of contact of these two tangents will always pass through one of two fixed points on PP prime. 13. Use the last theorem to solve the problem. Given 4 points P, P prime, Q, S on a conic, and the tangent at one of them, Q, to draw the tangent at any one of the other points, S. 14. Apply the theorem of problem 10 to the case of a hyperbola where the two tangents are asymptotes. Show in this way that if a hyperbola and its asymptotes are cut by a transversal, the segments intercepted by the curve and the asymptotes, respectively, have the same middle point. 15. In a triangle circumscribed about a conic, any side is divided harmonically by its point of contact, and the point where it meets the chord joining the points of contact of the other two sides. An elementary course in synthetic projective geometry. This book was written by Derek Norman Lehmer, Assistant Professor of Mathematics, University of California. It was published by Ginn and Company, Boston, 1917, and is now in the public domain. The text is available for free download at Project Gutenberg, read by Jim Renholt. Programming and illustrations by Jim Renholt, 2020. Corrections and comments are appreciated. Thank you for listening.